Hey guys, it's me, Miss Robert. Wow. Welcome to my channel. If you're new here, sometimes I make videos while I'm gone. So I have these notes for you. I know that I wish that I had more of an opportunity for you to write in some of the answers. So I'm going to go over all of this and really hope that you see it. These notes you might want for the test that happens in weeks. Here is the end behavior of a function. So I know you saw it last week on the Booklet. The degree, if it is even, meaning if it's an even number. So this will also happen with x to the fourth power, 6th, 8th, 10th, etc. If it is a positive number, that's our happy parabola. So if it's positive, it rises on the left and the right. And the end behavior, how we read this literally says, as x approaches positive infinity, meaning as we go to the right, the y values go up. As we approach x going toward the left, the negative x values, the function also goes up. If it's negative, it's down, down. So as x goes positive and negative, both of them go downward facing. There's our sad. So we're going to have now parabolas, but also quartics look like W's. I don't know, sextic. I don't know. Also look like that. And so for the odd ones, these odd functions, so numbers 3, 5, 7, 9, kind of honestly, I like to think of them as like a regular linear function. So x to the first power is just y equals mx plus b. It's linear. And this is positive slope. Like you guys have always known that positive slope goes up from left to right. It starts down low and it goes up high. So our positive, happy, I guess you could say, looks like a positive slope. And then all the negative ones look like a negative slope. This is the case when the degree, the coefficient, is any even number, positive, negative, or odd number, positive, negative. So here are all of the end behaviors, what they look like. You guys were doing up, up, down, 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 up, down, and they're just written differently here. A polynomial function has a degree of n, so something to the n power. And the turning points is n minus 1. So I'm actually going to draw some little pictures here for you. I need to turn this around, don't I? This shadow is really obnoxious. Whoops. X to the 5th power. So an x to the 5th power is an odd number, which means it's going to look like this, where it has two different directions. And when we talk about turning points, there are going to be 4 turning points. So if it's odd, it's going to go up from left to right, and the turning points might be like this. 1, 2, 3, 4. So one way to think of it is the number of turning points. Another way to think of it is how many zeros there could be. 1, 2, 3, 4, 5, if this was a horizontal line. But do you see that only 2 of them actually go through the x-axis I've drawn? So I've kind of made like a fake one. Those are 5 roots if they were shifted, maybe translated up a little bit. But right now there's only 2 real roots and the rest of them would be imaginary. So if there's 2 of the, 2 x-intercepts crossing here, I'll call those 2 real roots. And since this is x to the 5th, I would say there are 3 imaginary because they need to add to 5. So steps for graphing a polynomial function. Typically, you just need to plot the zeros and then just like do some swoopies through them. It is very hard to see like how high necessarily they go. You could do it, but it takes a lot of work. So in Math 3, you're only going to be sketching an approximate graph. So you're going to plot as many points as you possibly have, maybe make some extra points in between so you can be as accurate as possible. Plot as many points as you have and then sketch a graph. So Here is our note about multiplicity. Multiplicity is when there's like a double root or a triple root. And honestly, without even reading this, you guys can see here, root A has odd multiplicity, meaning it's just like one root, but this will also be the case if there are three, like a triple root. Double roots bounce. So even multiplicity, even numbers are 2, like double. You won't see very many quadruple roots, but if you did, it would also bounce off. So we call the multiplicity, odd and even also, but the more likely you'll see is when it's a factor by itself and then a double factor. So this could be the graph. I actually want you to write this down. If we were labeling this, they've labeled it A. So A is any number, but I might say A is -2, and then let's see, -1, -2, 1, 2, 3, 4, 5. Let's say B is 5. This could be a cubic function. I can see that it goes up, down, up. So I would say this is probably a cubic, which would be x to the third power. And that's easier here to write in factored form. So the factor for the root at -2, you know what it looks like. If the root is at -2, I have x plus 2. Here, if my root is at +5, I'm looking at an x minus 5, and because it bounces off, that's going to be a double root, a squared. So this could be the graph of this function. It's going from left to right up like a positive slope, so I know that I don't need to have a negative sign in the front. Yeah, other side. Woohoo, here's some practice with some real polynomial functions. All of these are in standard form, and you guys did your booklet where you noticed that the highest exponent is the degree of the function. So that's how many zeros it's going to have. Anything else doesn't matter. This is going to have 7 potential roots. Some might be imaginary, some might be real. And so I'm going to actually write that here into the degree for you. This is a degree 7. 7 is an odd number. And then the leading coefficient. So just like an A value, these coefficients in front of the largest x term determine whether it's happy or sad, positive or negative. So since this leading coefficient is 4, it is positive. And so when it says graph comparison, we're comparing this 7 maybe to like an x to the first power, a straight line, an x to the third power, a cubic swoop. And so the graph comparison might be like x to the 1 looks like that, x to the third looks like that. So I know that x to the 7th is going to have like way more wiggles, but it's still going to go from bottom to top. So this end behavior, one way to write it, of course, is just down, up. But this is, if you'd like to practice, this is how you'll also read it in a calculus class. You do talk a lot about as x values approach a certain thing. So let's see, from the x values perspective, the x values, we use this arrow to say approach infinity. So we read this as x approaches infinity, and that means that all the x values are going positive to the right side. So as x approaches infinity, if I looked at this graph and I went, I followed my thing to the right, those values are going up to positive infinity. So I'd say as x approaches infinity, the y values of the function approach positive infinity. That's my up. Now, I guess I should have done down, up in that order, but honestly, you could write them, I should have written it in a different order, but technically I'm still reading it the same way, so it's like, whatever. As x approaches negative infinity, meaning as the x values go negative, if I went backwards on this graph, they're going down. So as the x values go left, the function goes down, it approaches negative infinity. And that's how we would do each of these. If you wanted, of course, to pause here and try them, you should. I'm still going to walk through them with you, of course. For the next function, there are 3 terms, but the highest degree is 6. So this is going to be an even function, which means it's going to look more like an up happy parabola or a W or something like that. It's also negative. So in case you're wondering, the number doesn't matter. You don't need to care about the number. As long as you know it's positive or negative, the dilation is just too complex for us to worry about. So if you want to omit that number, it's not important. The 6 will be important though, because it tells you how many times it kind of woo-woo-woos. So our graph comparison for a negative even function might be like an x squared, like a parabola. That's even. And it's negative, so this is going to look something like a sad parabola. The W, you know, the W goes whoop, 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 like an upside down W. This 6 is going to go whoop, 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 and it's going to go down on both sides. But one of the reasons we call this end behavior is because we truly don't care what's happening in the middle. We know it's going to have some roots. Let's see, 1, 2, 3, 4, 5, 6, 7, 8. I just drew x to the 8th power. Negative x to the 8th power. But really all of the stuff that happens in there, it's important to like have an x-intercept. But when we say end behavior, we literally mean just what happens at the end. So I'm going to do a better job here of putting them in order. This is down, down. And I'm going to start with the negative values of x. So I read from left to right in math, so that makes most sense. But if we're, you know, down, down, I'm going to start with the negative values. So as x, we would write, as x is approaching its negative values, meaning going left, this function is also approaching negative values. It's going down. And as x is approaching its positive values, it's going to the right, the function is also going down. So I'm glad I gave you guys that booklet so you could maybe just practice like what the most important things are. So you know maybe just to read here. And that would be, you know, helpful and important. And hopefully by now you could do the third one on your own. I see x to the 5th is my largest. That is an odd number. And this one is negative. So it's going to mimic a negative slope. It's going to go like down from left to right. The end behavior is going to go down like that. When it says graph comparison, you don't need to do a lot of these, but I'm just doing them here for you. This end behavior, you can see, starts up high and goes down to infinity. So this is an up, down. And so as x approaches the negative values, meaning it's going to the left, that is going up, that y value. That function is approaching positive infinity up to the sky, positive. And as x approaches the right, as we follow it down and to the right, the y values are going down, down to negative infinity, down, 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 down. That's how we would draw that. Here, this is great, little practice. You don't need to worry about exactly where the roots are, but the degree of this function looks like 1, 2, 3. So this is a regular cubic. There are 2 turns, and when we say turns, we mean where the direction of the slope changes. And the direction of the slope changing causes these maximum and minimum points. These are not called vertices, which is the plural of vertex. We would not call that a vertex. We instead use the word extrema. So you're gonna hear this word also in Mathia. Extrema is the plural umbrella term for any maximum or minimum point where the graph changes from positive slope to negative slope or from negative slope to positive slope. So the degree of this is 3. I can tell it's a cubic. The degree of 3, of course, means it's x to the 3rd power. And the leading coefficient, you just have to write positive. Because again, we don't care what the actual number is for the dilation, just that it's a positive number. This one, let's see, I have a 1 direction, 2 directions, 3, 4. So there are 3 turns, which means this is a degree of 4. It's our W shape that points upwards. And since it points up, our leading coefficient is also positive. And finally, this one has 2 different directions. It's going from up to down, which definitely tells me it's a negative number. Let's see how many turns it does. 1, 2, 3, 4, 5. So this is a degree of 5. It's odd. And the leading coefficient, since it goes from up to down, looks like our negative sloped line. So this is going to be negative. Voila. Voila. In your book, after you do this, we're actually going to work with what those roots are exactly. And the factors that represent those roots. You'll see a lot of these are decimals. This one is at -3, -2, and 1. You can write this equation, and we're going to do that in the book. Incredible.